In this video, I'm going to consider collision in two dimensions. In previous video, one-dimensional collision was considered. Now, two-dimensional one. What do I mean by that? Let's say we have a couple of balls, M2 initially at rest, M1 is moving rightward at a velocity of u1. If I consider the collision to be one-dimensional, after M1 strikes M2, basically we expect both balls will move on horizontal direction. M1 may go leftward and M2 may go rightward, but still they are moving on horizontal direction. But if they have freedom to move in two-dimensional space, after the collision, the situation is going to be a little bit more challenging. Let's say M1 after the collision is moving at a velocity of v1, making an angle of theta 1 with horizontal, and v2 for M2, which is making an angle of theta 2 with horizontal. How can we deal with this problem? You remember I told you momentum is always conserved, regardless of the collision to be elastic or inelastic. Let's say before the collision, the momentum of the object number 1 is p1 and the momentum of the object number 2 is p2. After the collision, they will produce a couple of new vectors like p'1 and p'2. Let's use a Cartesian coordinate system to consider the problem. Conservation of momentum in two dimensions tells us that the total momentum in horizontal direction is conserved independent of the total momentum in vertical direction. So we have a couple of equations. The total momentum before and after in horizontal direction are equal. The total momentum of the system before and after in vertical direction also are equal. So conservation of momentum in two-dimensional space gives us a couple of equations. Let's say M1 has an initial velocity of u1 to the horizontal and M2 at the beginning is at rest. After the collision, they will generate a couple of new vectors. Here you see the velocity of the first ball as a vector like v1 making an angle of theta 1 to the horizontal, and the velocity of the second ball making an angle of theta 2 to the horizontal. Anyway, if I multiply each velocity by the mass, I will have the momentum. So basically, v1 can be converted to p1 like m1 v1. And v2 is going to be converted to momentum like p2 equals mv2. I'm not going to do that now. If I decompose the velocity, I can easily decompose the momentum accordingly. So let's continue with velocities. Here v1 will have a horizontal component like v1 cosine of theta 1, v1 cosine of theta 1, which is going to be the horizontal component. Likewise for the other one, I will have v2 cosine of theta 2. And now I can consider the conservation of momentum in horizontal direction. The total momentum before and the total momentum after are going to be equal. So here, be very careful. The momentum of the object number 1 is going to be p1x, which is m1 u1. The momentum of object number 2, it's at rest, it's 0. The momentum of the object 1 in horizontal direction after the collision is going to be b prime 1x, which is m1 v1 cosine of theta 1. And p'2, the momentum 2x, the momentum of the object number 2 after the collision is going to be m2 v2 cosine of theta 2. The total momentum in horizontal direction after the collision will be equal to the total momentum before the collision in horizontal direction. So let's put them equal. This is the total momentum before in horizontal direction. This is the total momentum after in horizontal direction. This is the first equation, and the second equation is going to be generated out of the vertical direction. Anyway, in vertical direction, also the total momentum before and after are going to be equal, but we have already simplified the question. Why? Because in vertical direction, I have no momentum before the collision. And normally, as before the collision anyway, I can easily suppose the motion to be on horizontal direction, I can easily remove the vertical direction before the collision by selecting a proper coordinate system. But after the collision, it's not under my control. So anyway, after the collision, I should decompose V1 again to the vertical direction like V1 sine of theta 1 here, and if it's multiplied by m1, it's going to be the momentum. Likewise for the V2, I will have V2 sine of theta 2. Now let's use the conservation of momentum in vertical direction. Fortunately, in vertical direction, according to our proper coordinate selection, I have no components. But in vertical direction, anyway, I multiplied this one by mass, and it's going to be the momentum in vertical direction after for the object number 1, and it's the momentum for the object number 2 in vertical direction. Being notified that here I have a negative sign, and this negative sign is a reason because as you see in this case, V2 sine of theta 2 is downward. So if I select the vertical upward direction to be positive, downward will be negative. So I have to use a negative sign here. Okay, so far we have already generated a couple of equations according to the horizontal momentum conservation and vertical momentum conservation. If the collision is elastic, also I can have an additional equation. So let's say when the collision is elastic, I mean no energy is lost from the system, then there is an additional equation from equating kinetic energies before and after the collision. It's the third equation. So here I will have the total kinetic energy of the object number 1 before the collision, because object number 2 was supposed to be at rest, initially at rest, there is no kinetic energy. After the collision, I have the kinetic energy of object number 1 and kinetic energy of object number 2. This is the third equation. Okay, so far we have 3 equations. The first 2 are always valid because of conservation of momentum. The last is just provided we have conservation of kinetic energy. I mean the collision is elastic. In math, in principle, we have 3 equations, so we can have up to 3 unknown variables. Anyway, let's have another additional condition. This additional condition is m1 is equal to m2. Let's say the 2 balls have the same masses, like snooker balls. So if I suppose that, I can drop a half of m1, a half of m1, and a half of m1 in the last equation. And so here I will have u1 square is equal to v1 square plus v2 square. So the 3 vectors can make a right triangle for me. u1 is the hypotenuse, is the initial velocity of the first ball. v1 and v2 are making the other sides. This format, or this right triangle, is just valid based on 2 assumptions. First, as it's the outcome of the conservation of energy, the collision must be elastic. And second, the masses of 2 objects must be the same. Let's answer this question. An air puck of mass 0.2 kilogram, let's say it's 0.2 kilogram, the first puck, collides with a stationary air puck of mass 0.3. This is stationary, initially at rest. After the collision, the second puck moves away with a speed of 0.5 meter per second. You see that. The paths of the pucks make angles of 37 degrees and 45 degrees with the original direction of the first puck. Yes, the angles are given. Part A, determine the speeds u1 and v1 of the first puck before and after the collision. The first puck has initial velocity of u1 or speed of u1, and after it's v1. I'm looking for both. I can easily use conservation of momentum and find these 2 because the question did not mention the elastic or inelastic nature of the collision, so I cannot use conservation of kinetic energy. Okay, look at this. Here, let's say this is P1 the momentum of the first spark after the collision, it makes an angle of 37 degrees to the horizontal. Here I have a P1 cosine of 37 degrees, the horizontal component. Here I have P1 sine of 37 degrees, the vertical component. Let's say this is P2, the momentum of the second spark after the collision. It's making an angle of 45 degrees to the horizontal, so it's P2 cosine of 45 degrees, and it's also P2 sine of 45 degrees. These are components of the momenta. Okay, let's use conservation of momentum in vertical direction. So I will have just P1 sine of 37 degrees, and here P2 sine of 45 degrees. You see them here. P1 is M1V1 sine of 37 degrees, vertical component of the first spark after the collision, and this is the vertical component of the second spark after the collision. I'm using the conservation of momentum in vertical direction because it's enough to find one of the variables, here V1. Why? I know M1 is 0.2 kilogram. I know M2 is 0.3 kilogram given here. And also I know V2 because V2 is given to be 0.5 meter per second. And angles are given. So I'm just looking for V1. So conservation of momentum in vertical direction is enough to find V1. Let's plug in the values and find V1 to be 0.88 meter per second. Then I can use the horizontal conservation of momentum. What do I mean by that? The total momentum before the collision is just the momentum of the first spark. So it's P1. Let's say it is M1 U1. And I know M1, but I'm looking for U1. After the collision, I have the momentum of the first spark to be M1 V1 cosine of 37 degrees, provided I have M1 V1, the momentum instead of velocity. And likewise for this one, it's going to be the other to be M2 V2 cosine of 45 degrees. That's all. Let's put them equal. Total momentum before, total momentum after the collision in horizontal direction. I found V1 in previous part, so I can import it here and then plug in the values, and this is my goal, U1. So I have everything except U1, and U1 is obtained as 1.2 meter per second. Part B, calculate the percentage change in the kinetic energy of the system. What do I mean by percentage change? Actually, the total kinetic energy of the system before the collision is K1. After the collision, the total kinetic energy is K2. Change in kinetic energy is K2 minus K1. New minus old. And then delta K over K1 is fractional change. I mean, change in kinetic energy divided by initial kinetic energy. And if I multiply it by 100, it's going to be the percentage change. Okay, so let's do it. Total change of kinetic energy divided by the initial kinetic energy. Of course, initial kinetic energy is just the kinetic energy of the spark number 1, because spark number 2 has already been at rest before the collision. Okay, here I have the total kinetic energy after the collision, kinetic energy of the first spark, and the kinetic energy of the second spark after the collision, minus the total kinetic energy of the first spark before the collision. This is the delta K. It's downstairs I have a half of mu1 square because this is the kinetic energy of the first spark before the collision. That's all. You can plug in the values and find negative 0.24. Negative 0.24 can be multiplied by 100 to be negative 24%. Why it's negative? Because normally the delta K must be negative. It's inelastic collision and the system will lose energy. So delta K is negative. A snooker ball moving at a speed of 1.2 meter per second collides elastically with another stationary snooker ball of the same mass. Same mass. Elastically means we can use conservation of kinetic energy. After the collision, the balls move apart in perpendicular directions. The path of the first ball makes an angle of 30 degrees to the original direction. This is 30 degrees. Okay, so if they are perpendicular, the other must be 60 because they add up to 90. Determine the speeds v1 and v2 of the balls after the collision. We are looking for v2 and v1, both. We noted that perpendicular means same mass. We already had a discussion about it. Okay, let's start. First of all, I can use the conservation of momentum in vertical direction. When I use vertical direction, actually, I can ignore this one because this is just horizontal. So in vertical direction, if I have a V1 like that, I have also the P1 like that. And the other is P2 here to the same direction as V2. They are perpendicular. More than that, here I will have a vertical component of P1, which is good. If this is 30 degrees, it's going to be P1 sine of 30 degrees. And likewise for P2, it is 60, so it's going to be P2 sine of 60 degrees. Okay, let's do it. Here I have actually P1, which is mv1, and the other mv2. As masses are equal, I can ignore these two. Okay, so sine of 30 degrees is a half, and sine of 60 degrees is square root of 3 divided by 2. If I ignore the 2 in downstairs, I can have v1 is equal to square root of 3 times v2. The other could be conservation of kinetic energy. Result of that could be perpendicular velocities. I mean v1 and v2. So if I take u1 here in horizontal direction, this is v1 and this is v2, and they are perpendicular. I already mentioned it and proved it. So here we can use the Pythagoras theorem as u1 square is equal to v1 square plus v2 square. Then let's substitute v1 for square root of 3 times v2. And so here I will have 3v2 square plus v2 square. It's going to be 4v2 square. And if I take a square root from both sides, I will have u1 is equal to 2v2. u1 is 1.2, so v2 seems to be a half of 1.2, so it's 0.60. And if I plug in v2 here, I will get v1 for 1.04 meter per second. That's all. Thank you very much. This video is done. Thank you for watching this video, and thank you for being with me.